In some problems, we want to take the derivative of a fraction, and to do that we use the quotient rule. Basically, we have the fraction with the numerator u, denominator v. These are functions of x that are given. The quotient rule says we get a fraction. In the numerator, I have the derivative of the numerator times denominator minus numerator times the derivative of denominator. All of that divided by the denominator squared. We can also think of this as u prime v minus u v prime. All of that divided by v squared. We can also write this in the primes notation. Says essentially the same thing. Instead of v and u, we have g and f. The way the quotient rule looks has to do with the definition of derivative, and I'll cover the derivation of quotient rule in a separate video. Here, let me just say one more thing about it. The derivative of a fraction is not the same thing as taking derivative of numerator and denominator and leaving it at that. This is very easy to see why that's not the case, even for very simple functions like x cubed and x squared. If I divide x cubed by x squared, I get x, and the derivative of that is just the number 1. Whereas if I take the derivative of f, I get 3x squared. Derivative of g, I get 2x. I can cancel 1x and left 3x over 2, which is obviously not equal to 1. Okay, let's now do the 6 problems. The first is finding the derivative of x squared divided by x squared plus 1. We go ahead and call the numerator u, call the denominator v, and use the quotient rule that says u prime times v minus u times v prime. Derivative of x squared is 2x. Derivative of x squared plus 1 is 2x plus 0, which is again just 2x. And then all of that gets divided by v squared, which is 2x squared, which is x squared plus 1 quantity squared. If we multiply through, we get the 2x cubed plus 2x minus 2x cubed. And notice that I get a cancellation to get the final answer 2x over x squared plus 1 quantity squared. In the second problem, we are taking the derivative of e to the x divided by x squared, and that means applying quotient rule again. We can call the numerator u, we can call the denominator v, and have in the numerator u prime times v, derivative of e to the x is itself, minus u times v prime, derivative of x squared is 2x. And all of that divided by the denominator squared. Now, squaring x squared gives us x to the 4th. And on top, I have a common factor not only of e to the x, but also an x. Pulling out that leaves me with x minus 2 for an answer in the numerator, and then I can even cancel out an additional x and get the final answer simplified. In problem 3, we want to figure out the second derivative of sine of x divided by e to the x. We take the derivative twice in this case. Second derivative is the first derivative of the first derivative, twice in a row. let's use the quotient rule to get the first derivative here of dy dx, where we, as usual, call the numerator u, call the denominator v, and go according to the formula. U prime, derivative of sine is cosine times v, minus u times the derivative of e to the x is e to the x, all of that divided by v squared. Notice that I can factor out a common e to the x and get a compact form in the numerator, and I get a cancellation. I have e to the x squared down here, e to the x on top over here, and so I'll get just e to the x. So that's the first derivative, and this also shows why it's a good idea to simplify the answer, because I'm going to have to take the derivative again, and it's much easier to take the derivative of this than of that. So let's move on to that next. Continuing, we found out that the first derivative was this fraction. Now we take the derivative of that again to get the second derivative. Again, we use the quotient rule. This time the numerator u is this entire sine, cosine minus sine, and v is e to the x again. So we do derivative of u prime is derivative of cosine negative sine minus derivative of sine cosine times v minus u times v prime. Derivative of e to the x is its then divided by v squared. And let's go ahead, simplify a little bit. I have an e to the x common. Let's pull that out. Inside the first parenthesis I have minus sine minus cosine. Second parenthesis I multiply the negative through, I get minus cosine, minus times minus plus sine. Here I get a cancellation of negative sine and positive sine. I also get to cancel e to the x with one of the e to the x's down below, and end up with minus 2 cosine on top and e to the x at the bottom. So the second derivative is a simple expression that you see here. In problem 4, we have the derivative of a trigonometric fraction, sin x divided by cosine x, with u sin x and v cosine x. We do the quotient rule. U prime, the derivative of u is derivative of sine cosine times v, again cosine, minus u times v prime. Derivative of cosine is negative sine. All of that divided by the denominator squared, v squared. Cosine times cosine is cosine squared. Minus sine times minus sine is plus sine squared. And since the trigonometric Pythagorean identity says that cosine squared plus sine squared equals 1, we get the answer 1 over cosine squared. A little bit of trigonometry can shed some light on what we are doing from a trigonometric point of view. 1 over cosine x is secant x, the function secant x, and sine x over cosine x is tangent x. So what we've just done basically says that the derivative of tangent of x is equal to 1 over cosine squared or secant squared of x. Speaking of trigonometric functions, let's do one more. In problem 5, we just find the derivative of secant of x. Secant of x is just 1 over cosine of x, so we use the quotient rule on this one. Derivative of secant, derivative of 1 over cosine. 1 is our u, and cosine is our v. Derivative of u prime is 0, derivative of constant is 0, times v minus u times derivative of v. Here is derivative of cosine, negative sign. This term drops out. Minus 1 times minus 1 is plus sign, so we get sine x over cosine square of x. Now let's write this in a slightly different form, which can be useful in calculus. I can write this answer as sine over cosine times 1 over cosine, an additional 1 over cosine, and that lets me get the derivative of secant as tangent multiplied by secant. In our sixth and final problem with the quotient rule, let's take the derivative of this fraction. If we delve into the quotient rule, jump in and try to call the numerator u and denominator v, then u prime will involve the product here of two functions, or a product rule. So it's a little bit complicated, but if you're a little careful, you'll notice that we can simplify this fraction first before taking derivative by simply splitting it into 1, 2, 3 fractions, as you see here. X to the 5 over 3x squared minus 3x cubed over 3x squared, and finally plus this over 3x squared. And then each of these things can simplify quite a bit. Here I can cancel out x squared with 2 of the x's and get x cubed left on top. Here the 3's cancel out and we are left with just 1x on top. Out here I'll cancel out the 3, be left with 2 on top, cancel out the entire x squared, and so in the end I'm left with this simple expression which has neither a product rule nor a quotient rule in it. And now we can take a derivative just very quickly. Derivative of this function, derivative of x cubed is 3x squared times 1/3. Derivative of minus x is minus 1. Derivative of 2 sine x is 2 cosine x. We can simplify this and get x squared minus 1 plus 2 cosine of x.